Welcome to Data Science with EJD. In this video, I'm talking about dimensionality reduction that falls under unsupervised learning in machine learning. In the previous video, we had talked about the first part of that, talking about PCA, principal component analysis, which you saw as a linear dimensionality reduction technique. Now, for TSNE, so in this video, we're talking about T-distributed stochastic neighbor embedding. That's t-SNE. So the question is, what is t-SNE, right? t-SNE or T-distributed stochastic neighbor embedding is a non-linear. So PCA is linear, right? But t-SNE is non-linear. It's a non-linear dimensionality reduction technique widely used for visualizing high dimensional data in 2 dimensions or 3 dimensions. It is especially effective at uncovering local structures and clusters in datasets where global linear models like PCA fail. So when PCA fails, or when your dataset is complicated or complex, you can come for t-SNE. So the key concept here, talking about dimensionality reduction, first of all, t-SNE reduces data from high dimensions, e.g., you can have a 784 dimensional data for something like MNIST to 2D or 3D for visualization, focusing on preserving local similarities instead of global geometry. Then for manifold learning, t-SNE assumes that high dimensional data lie on a lower dimensional manifold, and it seeks to preserve relationships between nearby points by mapping them to nearby points in lower dimensional space, that is. Then we talk about probabilistic mapping. Probabilistic mapping. So first of all, you talk about high dimensional space under that. You have similarities between points are computed using Gaussian distributions. We talked about Gaussian mixture model talking under clustering I think about 2 videos before now. Then we have low dimensional space. Similarities are computed using the student T distribution, and that's where it got its name from. T distributed stochastic neighbor embedding, right? So similarities are computed using the student T distribution to address the crowding problem, and then the algorithm minimizes the Kullback-Leibler divergence between the high dimension and low dimension distributions. All right, so the callback labeler divergence is given as callback P, uh, you know, I don't know what to call this. Is such that Q is equal to summation from I, where I is not equal to J. So I and J must not be the same. So you have Pij log Pij over Qij, like that. Then you have the key parameters and tuning. So you have a parameter called perplexity, and between it controls the balance between uh local and global structure, and typical values is from 5 to 50. Then the end component, that's 2 or 3 for visualization, whether you want 2 dimension or 3 dimension embedding. Then the learning rate, that's the common rate for the learning rate is 200 to 1000. That's too high leads to divergence and too low leads to slow convergence. Then n iter, that's minimum of 1000 iterations recommended. Now, n iter, is what you find in an old model of Python. So in new model of Python, it's actually max iter, maximum iterations, that is. So max iter, you have minimum of 1000 iterations recommended. Then you have init, initialization method, whether it is PCA is preferred, or you can say it's random. And the random state that is set for reproducibility. That's why we say random state equals 42 to ensure that we always get the same result without fail. Then common pitfalls of t-SNE, you have perplexity sensitivity. So the value of perplexity affects neighborhood size. Tuning is dataset dependent. Then you have random initialization. Results vary without a fixed random state. That, of course, that's why we do the reproducibility check by setting random state to 42. Then computational cost is zero, O n squared, O non-linear, right? Time complexity, which is slow on data sets with greater than 10,000 samples. Then the axes are meaningless. So if you have X, Y, Z axis, they are arbitrary. Only relative distances matter, right? Then you have the global structure. t-SNE preserves local structure, but may distort global relationships. All right. The whole essence is to get as much information as possible from the 2 dimensional form of something that is multi-dimensional, that is more than 3 dimensional for that matter. Then overinterpretation. Clusters can appear even when data have no inherent grouping, because maybe that is what you can consider as some kind of overfitting in machine learning generally. So How do we visualize t-SNE in 2D and 3D with Python? Let's start. Of course, you need to install dependencies like scikit-learn and plotly. If you followed me in the data analysis with Python, you would have been used to plotly, especially under data visualizations. But if you don't have that already, you just need to install scikit-learn and plotly. I mean, I've done it. I'm just trying to, I'm just doing it for your sake if you are new to this. So it's telling me requirements already satisfied because I already installed this before. But if you have not, you can go ahead and do that to be sure it's running. So we want to implement this on MNIST and Iris dataset. I think MNIST dataset is actually digits of handwritten digits, it's used for imaging like that, like some images of handwritten numbers, digits. Okay, so of course, we have NumPy, Matplotlib. Then we have the scikit-learn stuff where we load digits and load iris also. Then preprocessing, we need the standard scaler. You already know that when we talk about things like this, when we talk about dimensionality reduction, we need to do normalization of the data set so that we can get the best result possible. Then here we need from scikit-learn manifold, we need t-SNE. So you want to import Plotly Express as PX. This helps us to visualize in 3 dimensions. So here we are doing define t-SNE and plot. So we have X, Y, dataset name is dataset, perplexity is 30, learning rate is 200, end component is 2, random state is 42. Those these things we saw before. These key parameters we saw before. Now we are bringing them. Then you have normalization. So X scaled is standard scalar of fit transform X. Then apply t-SNE. So end component is end component. Perplexity is perplexity. Learning rate is learning rate. Max iter instead of the n iter we saw before is 1000. Random state is random state. Initialization is PCA. PCA is what you start with and then you build on that. Then XTSN is equal to tsne.feeder transform. This is where you train the model with the data. Now for 2D visualization, you come to all this. So if n underscore component is equal to 2, then you do a 2D visualization, and then you have all this. Then you also have 3D visualization. Elif, you have n component is 3. Then you do a plotly scatter plot like this and a 3D scatter plot. Then now in lines 40 to 42, that's where you talk about the two-dimensional revelation, the two-dimensional representation for the iris dataset. While we are using for the three-dimensional representation, we are using the load digits, which is the MNIST digits data set, right? So and then you plot that also. So if I run this, it's going to take a bit of time because it's a lot of process actually. So you see, it takes some time for that to come to be. Okay, waiting, still on it. Okay, yeah, the results are coming out gradually. So first of all, we have the t-SNE two-dimensional visualization iris datasets, where we need the 2D and 3D. So this 2D done. So 3D, some processes going on. So it's running through all these things, talking about 1000 iterations. That's gonna surely take a lot of time. So you have that coming still on. So we still have, as far as you have this asterisk, it means it's still running. Once a number shows, then it's done. So it's still on it. Okay, so you have the 2D visualization iris dataset. So you can see three clusters, right? Based on the color distinct, but then you have overlaps, and that's to show you that maybe there's no proper separation or there's noise or something around all those places. So you have the light, they are the smallest level. If you follow the color bar, then followed by the brown ones, which is it's something between 1 and 1.25, and then you have the very light green, which is close to 2 here. So the 3D is out too, okay? So for the MNIST digits data, so the first dimension, you have the second dimension and 3 dimensions. Of course, these are arbitrary, right? And then we have uh all this possible uh clusterings, as you can see. Okay, so this is this now. Color 2, this is color 2, this color 7, with all those dimension. One is, so it gives you the values for each dimension. Then you have all of that like that. So that's the beauty of Plotly. It's interactive, so you can go step by step. So this is color 3, and the dimension values are all there. So you have this, so you can just check it out like that. So That's us implementing that on MNIST and Iris datasets. So we see, how do we interpret the visualizations? When you have tight clusters, right? Distinct groupings suggest separable classes or local manifolds. So you can see this is clearly distinct from the ones up here. Now, without the coloring, right, it's difficult to know that these are distinct because you have some overlaps. But I mean, the color tells us they are actually different, right? Though they are not clearly separated. And you see, you can rotate this over and see what's going on. So that's the beauty of Plotly. You can see things happening over there. So if you want to know more on Plotly, you can check data visualization under my playlist on data analysis with Python. Then we have overlapping points. As we saw here, we have overlapping points, around this region. You can see some green lines are here, some brown lines are almost inside the green. So we have overlapping points like that. So overlapping points may indicate noisy boundaries or poorly separated classes. So obviously what we have up there is poorly separated, and they are probably noisy boundaries. Then shape of embedding does not preserve real distances, but interprets relatively. Then you have the 3D advantage. So for the plot linear, 3D advantage reduces projection loss and reveals hidden structure not seen in 2 dimensions. So of course we don't use this on the same data set. So we don't have, so it's hard to compare because this is on a totally separate data set. But I mean 3D can help you see things you couldn't see in 2D. Then t-SNE versus other alternatives. Of course, we have PCA, which you had seen before. So t-SNE is great for visualization and strong local structure. And the cons is that it's slow and poor global structure. It has slow and poor global structure. For PCA, it is fast, it is linear, it is good for preprocessing. And the problem with PCA is that it has poor cluster separation. Then UMAP, which you are going to do in the future, in the next 1 or 2 videos, we'll be talking about UMAP. It is faster than TCNE, but preserves more structure, but it is slightly harder to interpret. So if you need something better than t-SNE, that'll be UMAP, and I'll be talking about that later. And there's ISOMAP stroke LLE. That's the pros. It's good for geometric interpretation, but the con is that it is sensitive to noise. Sensitive to outliers. Then the summary. So it means the outliers can affect its results. Then in summary, what's the look at we want to look at some features and the value of this for t-SNE. That's T distributed stochastic neighbor embedding. The purpose, it is nonlinear dimensionality reduction for visualization. Input, it is high dimensional numeric. The input requires high dimensional numerical features. The output is 2D or 3D coordinate embeddings. It is best used for cluster discovery, manifold structure, or visual analytics. It is not ideal for global metric preservation and interpretability. The key libraries are scikit-learn.manifold.tsne, Plotly, and matplotlib from what we've done so far. So if you want to read further on this, so the person that came up with the whole idea, I mean, we have two people that came up with the whole idea of t-SNE. I think Hinton is one of the people recognized as the father of AI, right? And I think he won a Nobel Prize last year or something like that. So the original paper is from Van der Martin and Hinton, 2008. Then you can go to DistillPub, how to interpret t-SNE plots. Yeah, I mean, this interpretation thing is really important. Maybe I can even click it now to see. Then scikit-learn t-SNE API, UMAP documentation. We're still going to see UMAP later. So if you click on this, you may see how to use t-SNE effectively. Although extremely useful for visualizing high dimensional data, t-SNE plots can sometimes be mysterious or misleading. By exploring how it behaves in simple cases, we can learn to use it more effectively, right? So, this gives you a whole documentation on how to interpret t-SNE plots. So you want to make yourself comfortable with that by, of course, you have access to this code sheet, right? Just click on the link in the bio leading to the Google Drive and download all the code sheets and data sets. And then you can click on this by the time you put it on your computer, as far as you're on the internet, to take you to that page where you can get proper understanding on how to interpret T distributed stochastic neighbor embedding plots. So with this, we come to the end of this video. Thank you so much for listening. Let me know how helpful this has been for you, and if there's something you like want to try out. So if you have subscribed already, thank you so much for that. If you have not subscribed, please go ahead and do that, and be sure to hit the notification bell so you can always get alerted each time a new video is released. And of course, on my channel now, you can become a member. You can just click on join to see the possible membership level you can join to get certain benefits. So make sure you like and share also this video and other videos like this, so that more people can have access to this great content I have going on here. So if you need, if I've referred to something previously that you would like to know, like data analysis with Python, SQL with Python, or maybe even basic foundational AI, machine learning courses like statistics, probability, basic calculus, just check the description box. You'll find all of the links to the playlist. You'll find the links to the playlist in the description box. So till I come your way again, keep doing data right. Bye.